like Pierre works on reinforcement learning and applied to large language model. Before joining Cohere, he was like a PhD candidate at machine learning at CMAIP at École Polytechnique under the supervision of Stephanie Allison and then Awar Lepnek, and in close collaboration with Matthew guys. He was also part of the HECA team in Embryo, Paris. He holds a master's degree in mathematics and machine learning from MBA program in ENS Paris-Saclay. From January to March of 2024, he was a visiting researcher at Caltech in the computing mathematical science department, where he worked closely with Adam Willman and Eric Mazuba. So today he will give a talk about like his I guess like latest work on ShiQ, like bring back like Bellman's to the LLMs. So the floor is yours.
Yeah, thank you very much for the introduction, Tang. So yeah, for me that's a pleasure today to talk about recent work we did at Clavier in my team. So in Clavier, I'm working in kind of reinforcement learning RLVR team. We try to use reinforcement learning to fine-tune large language models. And so all this work is not only my work, but it's work with a team with different people. So I'm thinking of Yanis here, Nathan, Raphaël, Irem, Pierre, Omar, Olivier, Florian, and Mathieu work a lot on this project. So basically, I will just first summarize how we train like LLMs in general and where reinforcement learning is applied in LLMs, because like the idea of this talk is to find new algorithms to fine-tune large language models. So basically, in LLMs, if you want to train, you have different stages. So you have one pretrained stage where basically you take the entire internet and you try to predict the next token for lots and lots of data. And then you try to like focus on some specific domain using supervised fine-tuning. So basically it's just cross entropy loss. And then you try with this to like focus more on some specific domains such as math, code, safety, whatever. And then you have usually two stages of reinforcement learning. So one with verifiable rewards. So basically you want to try to use RL algorithm to fine-tune LLMs using true rewards. So for example, if you think at math, you try to solve math problems, and if your answer is true, you have a reward of 1 and 0 otherwise. And then you can also use reinforcement learning for like kind of fine-tuning LLMs for preferences. So here it's more like having access to reward models and not like a ground truth. You try to also fine-tune large language models. So in these two stages, you use algorithms to fine-tune large language models, and most of these algorithms are based on what I will call policy gradient-based methods. So using classical reinforcement learning and policy-based methods. So when you think about policy-based methods, I think most of you know some algorithms and methods for LLMs. So you can think as RLU, which have here, which is just a classical policy gradient and adding like relevant and smart baselines, which is leave one out. You can also think as CopyG, which is like less famous, but that's nice convergence properties in offline settings. So I will a bit talk about it because it's nice having properties here for ML theory of convergence in offline setting, or GRPO, which is like the most famous one here, which is kind of an adaptation of the PP algorithm you may know in reinforcement learning, but not having to learn a value network. So like, this is how like usually people are doing for fine-tuning LLMs using this kind of algorithm. So here I will mainly focus on algorithmic parts and losses for fine-tuning. So here are like some very small notations about what we are doing. So this is more like LLMs notation, and at some point I will introduce some reinforcement learning notations. So usually we have a prompts here for LLMs, and the thing is like then at some point you add some start of completion y, and you're completing in a large language model logits. So the output of your LLMs is logits, and so all you deal with from output of LLMs to a kind of reinforcement learning based approach is that you take the softmax of your logits, which give basically you a policy. So here you have probabilities, and you try to optimize this policy, which is usually what we are doing in reinforcement learning in general. Something which is specific in reinforcement learning is like we don't be like too far from a given reference policy, because usually when you are doing a lot of steps before, as I mentioned, some pre-train, supervised fine-tuning, you already have a policy, which is basically your output of your LLMs, and you don't want to be like too far from it. So compared to classical reinforcement learning here, people like to constrain a bit the problem of reinforcement learning, where basically you try to maximize your rewards, but you add a KL penalty here with regard to your reference policy learned than in previous stages. So really that's the kind of RL objective we care about here in general. And here I use KL because it's convenient, it has nice properties, but some people are studying other divergence in general. So what is the objective? I think you may know this, is just here you try to maximize the policy, which is just over the policy, which is just the expectation of this policy of your rewards minus the KL. So here, that's what people are doing in LLMs. And a very natural idea is to use policy gradient methods. Why? Because in LLMs, you already have access to this policy, which are basically just a transformation of your logits. So as you have access to it, it's super simple to like derive policy gradient. It makes sense in this case, and that's why people are using it currently. So yeah, if I just want to do a short recap on how policy gradients are like based on here, I'll just recall the RL objective here. So, and I define R pizza, the regularized reward here, where it's just one part of the KL. And the policy gradient methods is pretty simple. So it barely the same for classical RL objective or regularized objective. This is when you pick the gradient of your objective, you can rewrite it here and put the gradient of the log of your policy. So this is like pretty useful and well-known property here. Here it's slightly different because we are using regularization, but that's the same idea. And how do you do in practice? This is super convenient, as I said, because here you have an expectation. You can take Monte Carlo estimate of it, and then picking some here like B samples, you can just do Monte Carlo, and here you have an estimate of your objective. So this is super natural, and this is why it's so popular, because it's like super simple to implement. Just use an estimate of your gradient here using many batches, and you have a loss for like learning in LLMs. For those who don't know, but I think like most of the people here know it. So how to derive this? I will not enter into details, but it's just like it's called a score trick, and you can like really take the gradient for any given here parameter theta of your integral of your expectation here, and you can just write it at another expectation here, just using the fact that you can rewrite the derivative of the gradient of your pi theta, which is the measure you try to optimize here, as here pi theta times the gradient of the score here, and using this property, which is used in lots and lots of policy gradient in general. So I think you know this, you can do it. And like very two simple identities with this. I will not do a proof in my presentation, but I was just the only one I will do here. Is just that if you pick the expectation of the gradient of the score here, this is zero here, because here you can integrate your probability, which is just 1, and so this is 0. So that's the central property in policy gradient. Okay, anyway, so yeah, as I said, people, what are they doing in LLMs? They are taking the regularized objective here, and what they are doing is they just take the gradients. So as I said, it's pretty simple. You can do the same trick here, and you have the property that your gradient is simply this. Here, I just derive it for the regularized objective, but it's just the same thing. It's always the same property, and at the end, what you have is like that. Your gradient is your regularized rewards times the gradient of your score here. So very simple thing. And what are the pros or cons of these methods? when you think about it. Okay, so let's look at the pros and cons of policy gradients. So it's pretty simple because here you can like optimize any arbitrary rewards. So it's pretty convenient because your reward can be anything. It can be, is your math problem is true or not? So yeah, it's super convenient and arbitrary rewards. And this kind of KL formulation allows you to be like not too far from a reference policy and stay close to the data. So it's, as I said, in LLMs, that's a property. It's pretty interesting to have in general. And you can, as I said, like implement it like very easily with mini batches. But the cons of this is like, if you regularize too much, you will like be too close from your reference policy, and not too much. You can like drift and collapse in general when you learn in LLM. So this is something which is like well known. And you also have some reward and log ratio stability, sometimes which are not super useful because for some different path, especially for some architecture like MOEs, like mixture of experts, you can get some instability in this kind of ratio. So we need to be careful, but that's not like related to reinforcement learning. That's really like related to the KL formulation. And the cons here, there are many. So policy gradients without baselines, there is a lot of variance. So I think you know this. It's like a Monte Carlo estimates. There is a lot of variance, but no bias. So we need to like figure out how to fix this. It's not converging if you have samples which are not from your current policy. So you need to sample online to be unsure to converge. And I think that's one of the drawbacks. Sometimes if you get some fixed data sets and you can't sample, now like it's more common to sample a lot with RLVR, but at the beginning of reinforcement learning with LLMs, it was not so easy to sample. So yeah, there is some problems because you can't sample from the current policy. And even now, for example, sometimes you're sampling with like very difficult engines such as VLLM and stuff like this. And when you're doing this, basically, the current like sampling policy is different from the one you're trying to optimize. So it's still interesting to look at kind of convergence in offline setting. And yeah, you have the case of without rewards where you can use pairs of completion with GPU. I will not really talk about it, but the thing I really want to talk and focus on is about Bellman and some multi-turn environments. Because in classical policy gradients, so as I said, it's pretty nice because you have an unbiased estimate of your quantity. But the thing is, like, sometimes it can be like pretty long to learn because, as you may know, Monte Carlo estimates, you don't have a kind of a fine-grained allocations of the rewards or credit assignments because you don't like really know what pointy and local state and actions you used give you best result compared to kind of Q-learning based methods. So in terms of credit assignments, policy-based methods are not like so interesting. And this is why for example, in classical reinforcement learning, the success of Q-learning, for example, on Atari and these kind of things, because you have these credit assignments at some point to know where the information is. So what I will try to do here is I will try to derive new losses which are not based on policy gradient methods, but on a more Q-learning based methods to have this kind of credit assignment property, which can be interesting, especially in multi-turn settings. So I will define everything in general, but yeah. So currently, what I will say is like I will try to compare my methods and compare to kind of classical policy gradient methods that I used in LLM community. So that's really the idea, and I will try to see if I can derive losses with credit assignment, and I will explain this a bit more. Okay, so really shortly, as I said, the policy-based methods. So I will introduce the algorithm I need to compare with policy gradients. So I think you know, as I said, policy gradient-based methods, there is a lot of variance. So basically what people are doing, not only in LLMs, but in reinforcement learning, they try to subtract a baseline in order to reduce the variance of policy gradient-based methods. So how you can do this is because like I derive the first property here that for any baseline here, you have that the expectation of this baseline, if it's not depending on y, is equal to 0 here. You can just simply, in your estimator, subtract a baseline here in order to reduce the variance of your estimates. So that's something people are doing, for example, in actor critic, in reinforcement learning, or also in LM community in Erlu. And so what you can do is pretty simple. As you have this identity, then you can use an estimate of your batch and have an algorithm here. But what you need in general is like reduce the variance. And basically, the optimal the optimal baseline, it's always the same. This is your target. This is the expectation here of what you're looking for. So you're trying to find a baseline, which is your current objective. So it's not like really super. It's not a nice property, but basically, what you can do is like trying to find an estimate of the expectation of your rewards as a baseline, and that's exactly what exists is a so-called like leave one out baseline. So here, what people were doing in the LLM community with policy gradient-based methods was to subtract either the mean of your rewards because it's close to the expectation, or leave one out baseline. So leave one out baseline is very close to the mean, but it's slightly different. Is like for like different prompts, you use like all the other completions and the mean of the other completions on top of it. And at every time you leave one out for every completions to find a baseline. So it sounds like very nice property if one a baseline. So I will define it. So how do you define leave one by baseline? So basically you have a prompt here X and like K completions. So what you do is just you take all the different reward except K here, except I here. Sorry, for sample I. And this is why it's called leave one out. And if you do this, you can just simply put this leave one out baseline here in general, in order for sample I not having like too much variance. So this is just a nice estimate, a nice baseline. And why is this nice? Because it's unbiased. Yeah, go for it, Tang.
Yeah. So I'm just curious here. So like given a prompt, then you will generate like K different response here, right? Like the Y here is like we have like K different response, but for a given like prompt, which is like an X here.
Exactly. So for one prompts, usually people are sampling different answers because they hope that at some point you have one which is good and have good rewards, which give you some signal. And the signal come from basically the standard deviation of the reward for a given prompt. So, and when you do this, very shortly, this baseline is a good one because this is exactly the desired in expectation. You have the desired gradient. So I'm just saying that this baseline is nice because this is an unbiased estimate. So here, basically, you really reduce the variance while not introducing bias in your gradient. So this is like really a nice property, and people are using a lot RLU for this property because you have unbiased estimate of your gradient, and really that's something useful in general. And so you can prove that this term here is equal to 0 because it's not interesting, but you can look at it. And so really like the expectation of RLU is the classical gradient I present here for policy gradients. So you retrieve the classical policy gradient without an expectation. Okay, great. So once we have this, as I said, like it's also nice to converge in without being able to sample from the current policy. Here, in the real objective, I'm sampling from Y, which is sampling from the current policy. But at some point, for like lots of reasons, it could be like unpractical to do this. Take a simple example of offline or of policy is just assume you have sampled before some completions, but you can't like currently like having access to the environment. So your completions are offline, and so you would like to optimize from this, but you can't because you can't sample. And so here, what I said is that in online, you are sampling from your current policy, and in offline, you are sampling from another policy, which is basically here, mu, which is different from pi. And in this problem, policy gradient, if you are not able to sample from pi, you can't converge to the right solution because you can't have sample from this expectation, so you're not converging. And it can really have dramatic collapse sometimes in RLVR for LLMs or in classical reinforcement learning. And so one property I would like to highlight a lot, because I think it's super important, and especially in modern LLMs, like a training, is that, yeah, as I said, you can have like some data which is not from a policy. If you are sampling from different temperature, for example, with your LLMs, you're not on policy, so you need to correct these kind of things. And as I mentioned also, sometimes you're sampling from an engine for LLMs, such as VLLM, and so you're not able to have like fresh sample. You are still a bit of policy during your samplings, and for all this reason, you would like to correct these problems. And so what people are doing here with policy gradient, it's a very naive trick, which is basically to use what I call important sampling. So you can sample from a different policy here, but you can correct the expectation just having the ratio here of your current policy and mu. And this is called important sampling. And just doing this trick for the expectation, you have the right objective function. The problem of this is if you do this, it's not only in RL, but in statistics in general, you have lots of variance like in policy gradient. So you even add some variance terms here, which can be problematic. And so the thing is, it's great, and people in practice sometimes are doing it. If you look at, on the internet, on LLM communities, they try to reduce of policeness using important sampling. But the thing is, it also introduces variance at some point. But if you do this, you can still do mini batch like in policy gradients and have an estimate here. Okay, so why I present this here, and also for my algorithm after, is because you would like to be able to converge in the offline setting. So you can do important sampling, as I mentioned here, but I would like also to highlight something with air loop here. So I said recently a paper called CopyG. At the beginning, I present Airloo and GRPO. I think you have heard about it. And basically, CopyG is very, very close to Airloo. So here you have a baseline, and you subtract something here. And so this is a kind of loss which is very close to Airloo. And actually, for k is equal to 2 with Airloo, and if you sample from the current policy, Airloo and this loss, which is called CopyG, are the same. So why I'm saying this is because you have a very nice property in this paper, CopyG, contrastive policy gradient for LLMs, that you converge if you do this. So what I'm saying here is like Airloo, I mentioned, even if you're not sample from like online policy, but from different policy, we are converging in offline setting. So this is a nice property. So given offline data generated from like the same support than your reference policy, if you do and you try to minimize this loss here, CopyG, this is the same thing as optimizing the classical RL objective I presented at the beginning. So you're computing the right objective function doing this. So I think I had a question in the chat. Said, how to reduce the variance introduced by important sampling? That's a good question, actually. So maybe I can try to answer just this before. So a way of doing it is like people, what they're doing kind of truncated important sampling. So they try to, if this ratio here is too big, they clip. So if pi divided by mu is bigger, like let's say 2, 3, 1, you just put this value 1 or 2, and you upper clip this value that reduce, of course, the variance, but introduce some bias. So it's always a trade-off between variance and bias. So here, at least you're computing the right objective function, but if you want to reduce variance, you truncate it, and then you are biased. Yeah. So yeah, as I said here, a very nice property is like CopyG here. It's converged when you are not sampling with pi. So even if you have sample from a different policy, let's say mu, you can correct this off policeness in these two terms here. You can think as this is contrastive terms, and these two terms here with two sample y and y prime here, and this can you think as a bit the same as the important sampling ratio, but it's not a ratio. This is a difference here, and this is why you have a chance to have less variance. So, and like the main takeaway is like Airloo or like more like CopyG converge in offline setting, which is a very nice property in general. So you like kind of cancel the off policeness using this. A following question: is the base importance sampling. Is this base importance sampling awaited? Like copy G is not importance sampling. So this is like something I think is really beautiful. It's for me, at least for my understanding, this is the only methods which converge in offline settings without the weights. So this is why I think this is interesting, because you have a chance to converge in offline setting without having this importance weights, which are like which introduce lots of variance. So if you are interested, like, and want some loss, which have like nice properties of convergence without computing this, I think CopyG is like super relevant in general. So yeah, so what I said is like, even if you have off policiness, you can correct this with policy gradient, and you can converge in offline settings. So that's a nice property, but you still have the problem of classical policy gradient. Okay. So here, sorry, it was lots of things, but I present reduction of variance with RLU and convergence property in offline setting with CopyG, which is like barely the same with G is equal to 2. Yes, Jonas?
Yeah, I was just wondering, how does CopyG compare to RLU when K is greater than 2 for RLU?
RLU is basically if you have RLU with K greater than 2, so this is not CopyG anymore, and so. This is just more general, and you have more like variance reductions because your baseline is more accurate compared to the mean, but you don't have this property of how to say of contrastive, which helps you converging in offline setting, which is very nice.
Because I thought RLU was also unbiased. You said it was unbiased, so I guess
RLU is unbiased, yeah.
Okay, but now it's for convergence thing.
It's for convergence issues. Exactly.
Okay, I see. Okay, yeah, great. Okay, thanks.
And yeah, just to mention, so here I present RLU, which is unbiased, CopyG, which is unbiased too, and have convergent properties. But if you look at GRPO, I'm not saying it's great or not. I'm saying GRPO here, you normalize here with the variance of your rewards here, and you don't. This is not an unbiased policy gradient in general. So if you only think about like statistics, LMs are not about statistics, but like the statistical property of GRPO here, and you can do many batches, whatever, you have a biased estimate here in general. Here I forgot the clip of GRPO, but whatever. If you normalize here with the variance, it's not yet unbiased, and you don't have any convergent property in offline setting either with the GRPO. Anyway, so why I'm saying this also because after I will do comparison with RLU, CopyG, and my methods, and I'm not including in toy example this because it's not converging in any cases and it's biased. So yeah, just to mention it. Yes, Jonas?
Yeah, and I think there's been a bunch of fixes by the community of GRPO, right? Talking about the doctor GRPO, this kind of stuff. Is this also problematic with the fixes, or is it just like the original DeepSeek version?
Absolutely right. Like the doctor GRPO, you remove the standard deviation here, so it creates like unbiased estimate. You're absolutely right. But in general, but when you think about it, if you remove the standard deviation and not clipping, this is RLU.
Okay.
Well, anyway, at one sample, because here you leave one out, which isn't the case, but like very, very close to RLU. So at the end, I'm just saying that's the same objective function if you remove it.
Okay, great. Thanks.
Anyway, so I think DPO is just a case where you don't have a reward function. So basically what you are trying to do is just, you don't have access to a reward function. So the loss of DPO is just, you try to optimize an implicit reward here and decrease the likelihood of non-preferred reward here. I will not enter into details because I don't have time, but I think most of the people know DPO. DPO is another way also of optimizing larger goal models without rewards implicitly. Yeah, so let's do a summarize and explain what is good and what is not good. So here, I still want to, my goal is still to optimize this, which is a KL regularized objective function. Policy gradient methods are good because it's easy to implement. You can do many batches. You can converge in offline setting using CopyG. You can reduce variance with RLU or CopyG. And you can even like optimize without reward with DPO, for example, here, if you have pairs of completions. Okay, but all these things here are based on policy gradients. but there is no like kind of credit assignment, and they're all based on policy gradient. In reinforcement learning, you have an entire class of algorithm based on kind of Q-learning based methods, SARSA, Q-learning. And what I want to do here is like to adapt this Q-learning based methods to fine-tuning LLMs, because I think that even with I think it's an interesting question, like to see if we can derive algorithm like this, because in ARL it's super popular. And also I want to do this for doing kind of credit as assignment. I will explain before. In a sense, I don't want too long trajectories and do not know where the information is, but kind of find local information for doing good credit assignment. Okay, so maybe a short experiment or also to illustrate what I did here, because it was pretty long, sorry, is like for a stupid bandit with 3 arms here, you try to minimize the regret here. So you can compute the optimal policy, because this is a very simple bandit problem here with 3 arms. And what you can do here for like people with some more explanatory, as I said, copy deconverge to the right solution. Even sampling here, I'm sampling with not online data but offline data. Copy D, so it converges because there's the property of the theorem of this policy gradient. If you use here value reduction like RLU, you are not converging because you are still sampling not from the right policy, but at least you're converging to a good solution. Without value reduction, it converges to a very bad solution here. And here IPO is very close to DPO anyway. It's not the thing. But in bounded setting, copy G, you can converge to the right solution because you have this property of converging without sampling from the current policy. And here this is kind of offline bandits. And this is a LLM experiment on 7B models, so it's like recently small models. So this is from CopyG paper, and here we show that we can kind of optimize in offline setting better using CopyG than DPO, for example, for LLMs. So kind of policy gradient works well, but it's interesting to in offline setting take into account these specificities to convert to better solution. And here you can see that on test time on this is very toy TLDR dataset, you can having better rewards in general during learning. So this was just to illustrate policy-based methods here. And as I said in the last part of the presentation, I will try to find in RL, reinforced PPO, TD3 for LLMs at present, PPO, CopyG, GRPO. And in a classical reinforcement learning, DQN, Q-learning based methods, and there is no equivalent currently. So that's exactly what I want to do, is find kind of Q-learning based methods based on Bellman equations for LLMs. And so what I want to do is like finding algorithm that still take into account LLM specificities for having good performances. Because if you don't take into account LLM specificities with algorithm, you will not be able to have good algorithm and convergence. Okay, so that's the goal here. And what I call credit as assignment here is the problem of finding which past state action choices deserve credit or blame. When I'm saying this, like locally, which action and states you should pick at some point to be better in the Bellman equation. So that's exactly what I want to do. So here, some small notations. So they are very close to LLM notation. So usually here, I call S0 the states in reinforcement learning my prompt in LLM. And then I'm doing my completions. And so I have a new state, S1, S2, S3, where I add basically the completion here until EOS token. So you can like really rewrite this thing into a reinforcement learning problem, just concatenate the completion for having the next state. So really that's what I'm doing. And usually in reinforcement learning, you can either have a reward at the end of the trajectory, so this is super sparse, or sometimes some intermediate rewards in multi-turn settings. So what is multi-turn setting? This is the same thing, but here you have a user, a prompt. The LLM gives you a completion. Then you have a turn, which and then you discuss with the LLM in general. So you have a second turn, a user. You still have a completions, and then you have a second EOS token. So here you have an intermediate reward or not, but you have different turns. So you can like really frame multi-turn LLMs into reinforcement learning. Okay, so this is always the same thing. And what I want to do is use the kind of RL notation and RL Bellman equation to derive an algorithm. Okay, so why I want to do this? I want to do this for doing better credit assignment. So in classical reinforcement learning, you have what I call like state value Bellman equation and function V, which is the only quantity which respects this equation here, which is a recursive equation. And in policy-based methods, you are doing kind of Monte Carlo estimate here. So that is exactly what policy gradient do. So you compute the estimate of all your term, and then you do gradient descent here, ascent, sorry. And in TD learning or credit assignment here, this is slightly different because you only look at the difference between the next value function and the previous one here. And so the quantity used to learn is not the Monte Carlo estimate of all your return of your trajectory, but this is only here delta. And what we call this delta and credit assignment, because this quantity is exactly an unbiased estimate of the advantage and credits here. So if you have this quantity here, you know that the action A is better because you have a better return if delta here is positive. This is positive, A is positive, and you know you need to pick the action A if you are in state S. So this is what I call credit assignments. And in classical reinforcement learning, you have SARSA and Q-learning, which are exactly this, where you pick the information that in this state, you need to pick this action. This is great because you can converge faster and you have less variance than in Monte Carlo estimates, but on the other hand, this is a bias estimate in general. So this is why people are calling credit assignment in reinforcement learning. And I really want to do the same. So all I will do with LLMs is very simple. So let's derive kind of Q-learning based methods for LLMs. So what I'm doing here is just simply taking the Bellman equation. So this is the Bellman equation for my LLM for S, all the action and next states. So here's like slightly different equation because it's a KL regularized Bellman equation. So this is the Bellman equation, but you have a closed form of the max here because you regularize with a KL for your policy. But you can really think as the Bellman equation for KL regularized things. So this is exactly my Bellman equation here. And what people are doing for their deriving kind of a DQN or this kind of thing. So they pick the right-hand side of the equation, they put it here, and you have a loss. So a very naive approach to derive kind of Q-learning based methods is just picking your quantity here, you put here, and you take L2 norm here, for example, or a square, and you have a loss to learn Q functions and then the optimal policy. So really, that all people are doing in a DQN for deriving the loss. But if you are doing this in LLMs, it doesn't work, and I will explain why. And I will try to explain kind of the tricks we need to apply to have this loss work. So here, what I call L try loss is simply taking the Bellman equation, putting all the term equal to 0, taking a square, and this is this. Okay. So this is all I derive kind of Q-learning based methods for LLMs. But if you do this, as I said, it doesn't work. So we need to apply different tricks to take into account LLM specificities. So here I've just recall the loss. And what I will do is why it doesn't work. Let me explain why. So first of all, if I do this, if I want to sample from this loss, I need to both load kind of the reference model of my LLMs and my current policy, my current LLM. So I need to load like 2 models during sampling, which is like unpractical. So basically, you don't want to load 2 models for like kind of engineering purposes. Otherwise, it's very difficult to optimize something. And in this loss also, it has a very bad property. It's like the initialization is very bad because in LLMs, basically you start from PyRef, which is the policy you have from your reference policy from SFT and pre-trained stages. And here the loss is not 0 at reference at initialization. So it means that your loss, there is some signal even if you don't have any rewards. So that when you try to optimize the loss, you like that when you have some signal, you want to take into account the signal. But if you don't have any signal, so here, if you have no rewards here, and you put kind of the policy here, I will try to explain, the loss is not 0. So you want like to take into account a bad initialization for LLMs. And also the last thing, why it doesn't work is because in LLMs, compared to classical reinforcement learning, you only have reward usually at the end. So it's like super sparse reward. And so it's super hard to optimize sparse rewards in general. So for all these three reasons, we'll apply like 3 different tricks. And usually it's kind of shift. This is why I will call ShiQ for shifted Q learning. And so I try to take into account engineering problems, optimization problem of initialization, and sparse rewards. And applying all these 3 tricks, it will lead to a loss, which can work for LLMs. So I start from my loss, which is a naive L2 loss of starting from Bellman equation. And I apply these 3 tricks. I will show in the loss where these 3 tricks change the loss to obtain my final loss, which is called ShiQ. So it's a bit tricky like this. So basically, but all the tricks usually are just kind of change of variables mathematically. So it's very simple from a math point of view. But the idea of this change of variable are to take into account LLM specificities. So yeah, Younes?
Yeah, just to clarify, because I'm a bit lost with the Q values. Are they given by a neural network, or like how do you? Okay,
that's a good question. So like, and all the idea here is like not computing Q functions, because it's the same in GRPO, for example. You don't want to have a target network because it's super costly, and we are still learning lots of things, and the reward is very sparse, so you don't want to learn both the target network and a policy target with just only one final rewards. So all the trick of ShiQ is also not learning Q functions. I will explain this before. Okay. So here, at the end, I will not learn Q functions because it's very difficult.
Okay.
And so, yeah, here, like to see, I'm starting from this loss, L1, and let's see the different tricks that change the loss. So as I said, I don't want to load the reference policy and 2 LLMs during learning at sampling time. So I'm just doing this change of variable here. And this term, like there is a transformation here. For like optimization point of view, I'm just adding a kind of a shift here to not start with a good initialization point. So this for like kind of optimization purposes. And for like tackling the like sparseness of the rewards, I'm doing multi-step extension. So what is multi-step? Multi-step is not only trying to find Bellman equation only the next actions, but like trying to find the reward at the end of the trajectory. So I'm doing multi-steps here extension in order having signal in a sparse environments. And using this 3 tricks, so it's pretty like tricky with a slide here, but you can look at the paper if you're interested. So I'm applying all these tricks to derive the loss, and at the end, I have a loss which is multi-term, or like having good propagation of rewards, a good initialization starting from PyRef, which is a pre-trained model, and without having to load too many networks at the end. And even doing all this transformation, I can say, like in CopyG, that my loss ShiQ, if you're doing this, you optimize the classical reinforcement learning problems. So at least, even if I'm doing all this it looks engineering tricks at some point, but at the end, if I look at this loss, ShiQ, it's still computing the right objective function. I can't say it's a kind of sample complexity or whatever, but at least I'm computing the right quantity. So if you optimize ShiQ, you're trying to find the best function of the RL objective. So this is while having chance of being better because you take into account LLM specificities. So let's it's a bit difficult like this. So let's do a simple example. So I will retake a bandit before LLMs for having intuition. So I take the same bandit experiment here. So 3 armed bandit regularized, and I still in offline setting, and I still want to find the best policy. So I try to minimize my regrets, and as before, CopyG convert to the right solution in offline setting. So no changes. DPO doesn't convert because you're not sampling from Bradley-Terry model. And ShiQ also, according to this theorem, converge to the right policy. So like in all the Q-learning-based methods in RL, they are converging in offline setting. And this is the same for ShiQ because it's also based on Bellman equations. So even if I'm not like sampling from my current policy, I can still optimize the RL objective and converge. So for at least I can see with bandit that my loss and my theorem is true because the regret tends to 0. So at least I'm computing the right objective function, but the interest is in LLM setting, not in bandit. But something I would like to highlight still in a slightly less toy example is a very simple MTP. It's for like explaining the credit assignment thing. So here, the goal is in a 5x5 grid, starting from here. The goal is to reach like the final case here at 7. But the thing here is like here, you don't have any rewards. This is super sparse. Okay. And the second experiment is the same, but here I have an intermediate reward of 3 here, and the final of 4, right? And so the question is like, can you optimize this using ShiQ, copy-G, classical policy gradient methods? So it's super simple thing. So I'm using kind of linear neural network. And the question is like, can you learn this? Okay. And here I will see the credit assignments. And when I'm saying credit assignment is like, if you're here, if you know that the reward at the end is 7, is fine. But if you're here, if you're doing Monte Carlo estimate, you have no clue that going right, if you're here, give you the 3, right? Because you only have the information of the sum of your entire reward. So if you have a reward of 7, you don't know how you obtain 7, right? With policy gradient. Because when you do Monte Carlo estimate, you do this, for example, for 7. And so you don't really know how to obtain 7. And this is exactly what I've obtained here. So here it was just for final rewards. So as before, ShiQ and copy-G converge to the right solution in offline setting. So this is great. But here, both methods converge perfectly. But here, with fine-grained rewards, so here this is the second cases with intermediate rewards here. See that copy-G, so the policy gradient, doesn't have a regret that tend to 0. And so here, for example, copy-G is able to find the reward equal to 4, so the final rewards, but it can't find the path to find the intermediate rewards of 3. So in multi-turn setting here, I'm showing that the Q-learning-based methods converge faster to the right solution because the regrets tend to 0, compared to classical policy-based methods where you're stuck in a minimal, in a local optima, where you don't really know how to find the best reward here, and so you're stuck here when you try to optimize in a simple MTP. And so what I want to do here is I want to leverage this intuition in LLM settings for multi-turns. So what I will try to do is finding some task in LLM setting where I have some intermediate rewards, and so where policy gradient method, like GRPO, these kind of things, struggle to find the good path, and where the information is at some point to convert to the right solution. Yes, Jonas?
Yeah. So sorry. So can't you add entropy term, for example, to avoid these like local minima issues?
You mean do you, for example,
max,
people? Yeah.
Max RL also, these kind of things.
Yeah. So some people are adding some. Here is not a. This is still an example. Here is like here the graph here are like the 5x5 grid, so it's not LLMs. Huh? It's really this, and even in simple example here, you see that policy gradient method doesn't converge sometimes, and it seems surprising because theoretically they're supposed to converge, but you don't have the information where you have this fine-grained allocation. Even for a 5x5 grid, if the policy gradient finds the reward of 4, let's say like this, and then it's still stuck and try to optimize this path, and doesn't really look for to optimize the best reward here. While with ShiQ, you have the advantage of, if you're here, you have the information with credit assignment that you need to go here. So at some point you have more information because you can leverage kind of local information compared to classical policy gradient. So that's really what I want to illustrate here. I will not talk about here Pareto front, whatever, but you can optimize the reward without having a to be KL, which is a desirable property in the LLM setting. And so here I will try to adapt in multi-turn the loss I present to you, so copy-G and DPO. So here's like slightly different versions of DPO and copy-G. So these are the two loss, but here you have kind of all the different actions and rewards over the entire trajectory. So it's kind of the equivalent of multi-turn copy-G and DPO as a baseline to ShiQ for LLMs. And here I'm using a HH dataset to optimize rewards. So here is this LLMs task, but single turns. Where some say single turn is I only have rewards at the end. So no intermediate rewards, just reward at the end, like usually in math, in safety. So this is kind of classical LLM task. And here, this is offline. You see that DPO is able to optimize the trajectory, DRO is another algorithm, whatever. And CopyG performed pretty well of optimizing the reward here, but as it's expected, because it's like designed to be good at like kind of fine grain and not fine grain, sparse and final rewards. So policy graded methods, for example, here CopyG perform pretty well, and so even a bit better than ShiQ here. So is this expected? Because you can't beat an algorithm which is designed to be on this task, right? And so I'm not saying policy gradient are not good. I'm saying they're like super designed for final rewards setting. But as long as you have kind of intermediate rewards, which is this case here. So here this is a slightly modification of BFCL, which is an agentic benchmark for LLMs. And this is multi-term. And so if you can craft kind of intermediate rewards for LLMs in this agentic benchmark, here, ShiQ is able to leverage this fine-grained rewards to do some good allocation, some credit assignments, and perform better in terms of optimization of the reward than classical CopyG methods, for example, here, or DPO. So what I'm saying is, like, I'm not saying like policy gradient methods are not good. Of course, they're good and they're super simple. It really makes sense. What I'm saying is, like, if you get some more and more difficult environment with fine-grained rewards, agents that need to tackle, and having some specific rewards for a given term, here ShiQ makes sense because you can leverage this fine-grained allocation at some point to optimize the rewards. And that's exactly the same thing with, for example, very long Atari, for example, DQN and Q-learning-based methods are good for DQN, but because at some time you can pick connections that give you a reward at the intermediate and not at the end of the trajectory, which is pretty long. And here, Q-learning-based method makes sense, and this is exactly the same idea for LLM in multi-turn. So if you're trying to optimize single-turn LLMs, I'm not saying use ShiQ, no. Use classical simple algorithm. But if you have something fancy with intermediate rewards, and currently it's not always the case, but I think it will be more and more the case with agentic LLMs, agentic benchmark. Here, I think ShiQ can make sense and optimize better the rewards here. So that was really the main takeaway of this talk, is we want to improve like LLM learning using Q-learning based methods, using multi-step extension, good initialization. And here in my method, I only have one network. So like in GRPO, Erlu, guidance. So it's not more, it doesn't require more computation than classical policy gradient methods. You hear something which is different, say, compared to other methods, such as CopyG, where you need like 2 pairs of completion, or Erlu, or so here you can only optimize single trajectory. So it's a good property also. And yeah, so it can be both adapted to single-turn and multi-turn reinforcement learning. Okay, and so what I'm saying also is like this loss. This I use it for LLMs because I work in Clavier, but you can also think as using this loss for optimizing offline reinforcement learning. For you can think that Mujoko, for example, or Mujoko offline, not the classical one, or like other tasks, because actually this is a loss that converge in offline setting, which is based on Q-learning. So I think it could be interesting to try. And for distillation also, you can maybe try to find new way of doing kind of trajectory distillation with ShiQ loss, and that's the kind of thing I'm currently working on. So yeah, to summarize, the idea was like to derive new algorithms for fine-tuning LLMs, which are slightly different than policy gradient-based methods, and have a chance to have a better credit assignments, fine-grained allocations at some point, even if currently the number of applications where it's the case are limited. And I think ShiQ can really make sense if there are more like multi-turn LLMs applications. Yeah. Is there any questions? Yes.
Who goes first? Oh, sorry, there's a question in the chat as well. But, yeah.
Ah, sorry. What is the limitation of ShiQ? Very good question. So first of all, as I mentioned, I don't think this is useful to use ShiQ if you have single turn. If it's single turn, this is bandit. Bandit is single turn. Just do a kind of, I don't know, DPO, GRPO, Erlu. I will more recommend Erlu because the GRPO, the clipping is a bit tricky sometimes. So do something simple. but the limitation of ShiQ is definitely that it's a bit too fancy, and so you need a lot of tricks to have a Q-learning-based method that works. So if you do simple classical reinforcement learning, don't use ShiQ. So it's not the limitations; it's more like use the right algorithm for the right purposes and benchmark and application. So yeah, first limitation of ShiQ, I would say it's a bit more too complicated if you want to do simple single term. So for me, that's one of the limitations. And I think in these cases, as I show here for H datasets, it's not better than policy-based gradient methods. So this is one of the limitations of ShiQ. Maybe another one. I like it because you don't need like pairs of completions. So if you only get, let's say, one, so it's not a limitation actually. It's more an advantage here. Sorry, I'm a bit biased on this point. But as it converges to offline setting, I think it's also an interesting property that can be used in general to converge. So yeah, so for me the main limitation is I think it's a bit more complicated, and also I can recall it. If you look at the loss, this is a token level loss. As I said, here we are summing of the trajectory here, and I think you don't need like kind of token level loss are interesting here for multi-ton settings for having this local information. But same as I mentioned, if you don't have information at the token or multi-ton scale, don't use kind of multi-ton token level loss, because this is too complicated compared to classical loss. Yeah.
Like, so I'm just like I think I'm a little bit lost in the multi-turn things.
Yeah.
So like as a concrete example, so it's like it's kind of like a conversation between like the LLMs and humans, right? Where you ask a question, they give a response, then the multi-turns will be like, it will treat it like the next conversation as well, right? It's kind of like concatenate the whole chats together, right?
Exactly. Let me give you a very simple example of multi-turn here, RL. So my question is like, okay, can you book me a ticket to go by plane to Canada to visit University of Alberta? Okay. And so, for example, the LM will first, I don't know, go through, I don't know, Google Flights and said, okay, I'll find this flight. So if you're able to find a flight, you have a reward of 1, but you didn't book my flight. So I can say, okay, now my password of credit card is blah, blah, blah. You're able to pass this. So here I'm answering. And then if you're able to find and book the plane tickets, you have a reward of 2, because you either able to find the right tickets and pay. And so here, basically, this is an application of agentic agentic LLMs, where you can have a finding and reward because you have 2 different tasks, but the goal is like to solve all of them at the end.
I see.
And this kind of application can make sense.
Thank you. And also, like, maybe I missed it, but like, are there any exist like during your papers or during your projects? Are you find any like maybe particular NLP data set such that like the previous like policy-based methods, like it's not so good, such that like you kind of really need for those, and then like maybe one of the reason why it's not so good is because of those like credit assignment.
Yeah. But on BFCL-V3, which is quite popular, I obtained better results. No, not here, which is where I craft kind of finding and rewards here, because you have multi-turns, so you can have finding and rewards. So here I found that it's better. But as I mentioned, it's pretty rare currently having some finding and rewards in LLM settings. And yeah, and we need, but I think it will be more and more common, as I mentioned, with agentic things.
Okay, sounds good. Thank you.
Another question? Yeah, Colin?
Yeah, thank you very much. So probably just a quick question about kind of computational complexity for the ShiQ compared to the previous algorithms. Any comments about this?
Yeah. So about it's a very good question. So about so in terms of in terms of memory, this is basically the same than classical token level loss, such as GRPO, for example. But here you may think it's more in terms of flops, more computationally than classical policy gradient. But this because you have to sum, but in fact you can be smart and avoid it, because this is inverse cumulative sum. And so basically, if you start from the end of the trajectory, you can compute it this term pretty easily, and then you sum. So in terms of flops, it's like really equivalent. That's not the bottleneck of ShiQ in terms of flops. So the computing of the loss. Basically, it's like really the same time. And in terms of complexity, it's not squared here, even if you have to sum, because you can just first do this sum and then sum at the end.
Yeah, thank you.
Yeah, like this is look a bit scary. I agree, but in fact, it's not too long to compute the lots. If you do it smart and compute inverse cumulative sum here, starting from the end, and then you compute this term, and then this term plus t minus 1, and then at the end you sum everything. It's fine.
See. Cheers. Thank you.
So just to clarify, so the AKs here are tokens, right? Is it right? So because okay. So you assume you have a full trajectory, and then you compute from the end to I see.
Yeah. Otherwise, if you doing not smartly, I agree with Collins. It's not great loss in terms of complexity. But if you're smart here for computation, so you trunk, but you need memory. But at least you need the logits, in terms of space for your LLM. So you already have lots of memory, have all the logits. So I mean, having one or two when you compute the inverse cumulative log sum here, is nothing compared to activation in LLMs for memory.
Okay, great. I had a little question about trying to understand the intuition of why it doesn't work as well as policy gradient methods for singleton. Because so if I understand correctly, what you're doing right now is some sort of a Q learning, and I don't. I mean, the point of the Q functions is to, as you said earlier, right, like to sort of have a prediction of on the advantage. So if you only have a reward at the end, it should still be helping, right? Unless I'm missing something.
You mean if you have final rewards? Yeah. Here, the fact that you are doing multi-step extension with ShiQ, you can propagate well the rewards to the tokens. And in fact, here, I agree that copy D is better here. It's increased faster. But I did like lots of experiments in general, and the main takeaway is like ShiQ is comparable to policy gradient based methods. After it's a question of is it easy to tune for beta, and at the end, I would say it's mainly comparable. So you can optimize it, and compared to other policy-based methods in offline setting, you can converge to the best solution, like in CopyG. So I think in offline setting, it can be better than classical RLU, for example, or I don't know, GRPO, because you can converge to the right solution. But compared to CopyG, I would say it's mainly equivalent. But while I think it still adds some extra complexity. And for this reason, I do the simpler things, and policy-based methods in singleton are simpler. So yeah.
Okay. Yeah. Great. Yes. Great. And I was wondering, like, if you use now, so this was for the singleton, and for multi-ton, it's advantageous. But if you take policy gradient methods and you add entropy term, well, the question I kind of asked earlier, but I think I didn't ask it very well. But like, I get it. You do some sort of maxent RL, for example. Wouldn't it be better, on multi-ton?
In terms of exploration, maybe. I mean, you do not have the information about where it's better. In terms of credit assignment, it's not better adding some entropy. It's better for exploration, maybe. With you. So maybe you're less stuck to minimal optima where you find it. So that's maybe an example. I agree with you. But I'm not a big fan of adding entropy in LLMs because it's deterministic. It's just my own point of view. I know some papers, companies are doing it sometimes. Because why? Because it's deterministic. So why do you want to add in deterministic environment some noise? You could sample random tokens sometimes. So it can help, because if you decrease too much entropy, you can have collapse. So like for many reasons, people are using it in LLM. Personally, I'm not a big fan of it. But,
Are you saying the environment is deterministic, or are you saying because the environment may not be deterministic, right? You can't predict the user, or even the tool. If the tool calls, maybe sometimes they're not deterministic tool calls or something. Is it?
Alors, as a user, I agree,
Okay.
but currently, I didn't really know environment which are like really stochastics for LLMs. Maybe there is. It's like that are really like stochastics. It's not like so obvious for me that environment are stochastics, and that for me that's mostly deterministic. And tool calls, maybe you're right. You try to call a tool, and maybe you don't have the right one. But currently, I don't know tools. Maybe, for sure there is. But I didn't find any application at the time I was doing this with stochastic, and that was a bit my idea at the beginning. Was okay, let's try something stochastic. Maybe it's better, but I didn't find any environment which are like purely stochastic.
Okay, interesting. Okay.
And maybe there is. I'm not saying, but if you do a tool call, if you do it well, usually you do the tool call and you just have the answer. It's not stochastic. But
if it's verifiable reward, right? But if it's I don't know, like you're asking for I don't know the star. I don't know if you have a LLM judge that you could it's really hard to predict. But I agree. Okay, I see.
No, maybe for sure you can derive environment with stochastic tools. I think there will be already there is some thing, but at the time I was doing it, I didn't find any.
Okay, great. Yeah, thanks.
I think I have like maybe one last questions. I still try to understand like about how you can remove the queue. I think it's like you say that we only need like a single
and
you don't need a tiring networks basically.
So I didn't mention it, but I think that's maybe one of the most important parts of this presentation, this question. So all the tricks for not having a target network is to over-parameterize and using regularized Bellman equation. Because if you do regularized Bellman equations, what is the relation between Q and pi? This is this. So basically, your Q function is just the softmax. This is the logits. So your policy, your Q function, so you have another parameterization. So this is Q you can see as the logits. So basically, the logits, the policy is the softmax of the logits, and you have this over parameterization, which is only the case in KL regularized Bellman equation. If you use classical Bellman equation, you don't have this form, you don't have over parameterization and function linking logits to policy. Sorry, and so really that's the main point for not having to get a second value network is like dealing with KL regularized policy. So that's really all the trick. This rely on this expression.
I see. Okay.
It's because you have an over parameterization of your equations, and you can link the policy to the logits. Otherwise, it's impossible.
And then on the next slide, I think there's a slide where you replace the Q with the V. I don't know, maybe the next one. It's like I think you say that you can. Yeah, this one I think. Yeah, like here, it's like you replace like the Q with the V ref, which is like the thing. It's like so you have like some reference data already, and then like you try to use those like offline data, and then you can already estimate the V already, right? Yeah. It's like you can estimate the pi, and then therefore you can estimate the V. Yes.
And as I said here, I'm not computing value network. Value is just the max of my logits. Like the closed form of the expression I show mathematically. So really, this is a trick for not having value network. And here I'm dealing with V, which are like the logsmexp of the logits. But yeah, like the main takeaway is like you don't need value network, and this quantity arise here. So I'm writing like this because it's more convenient. I'm only dealing with logits.
Yes.
And maybe last thing is look here. I have a sum of squared terms, and usually classical policy gradients they have, for example, copy G. They have if you invert the sum and the squared. Basically, you have a kind of a more policy gradient terms without the fine grained allocation. So really, it's just inverting the sum and the squared in the loss. It's a bit tricky, but really, yeah. It's a bit tricky like to explain like this, but if you look at the paper in appendix, I'll try to talk a bit about it. Yes, Jonas?
And very, very quick, because I'm mindful of your time and before we need to go. That's super interesting what you said earlier about the link between the optimal policy, like you have like some sort of Boltzmann kind of, yeah, exactly this thing. I think, let me know if I'm wrong, but I think this thing, yeah, you said, oh, this is because you have a KL regularization, but this is only true if you have a deterministic environment. Is it right?
Yeah, my proof in the paper is in deterministic environment, but you can generalize it.
Because I have a vague sort of recollection of I saw some sort of equivalence like this in Bayesian control.
Mm-hmm.
They used to say, okay, the proof only works because the environment is not stochastic. If it's stochastic, then it becomes much more complicated. But maybe I'm not remembering well. But yeah.
No, it's still true for non-deterministic MDPs. I think that's doable. I was thinking about it at some point, and I think it's possible to adapt it to.
Okay. Okay, so it's not okay. So it's not a big because it's not a.
And maybe the difference with control is here, like this is discrete things.
Say it again.
This is discrete actions and states. So maybe if you get continuous action and state, maybe it's not true anymore. I don't know. Maybe that's why of the reason in stochastic is more difficult in control with continuous. I don't know.
Okay, it could be this. It could be this.
Maybe I'm not an expert in control at all.
Okay, great. Yeah. Thanks.
Yes, Clemens?
So sorry, that was a mistake.
Okay, no worries. Is there any questions? Yeah. So it was already lots of questions.
Yeah.
Thank you very much for all the questions. It was very, very nice having you.
Yeah, thank you very much for the talk. Yeah.
Thank you.
Thank you, Pierre.
Okay. So if no one have any other questions, so okay, let's thanks Pierre again, and thank you for coming and give a very great talks. Thank you.
Thank you very much.
Bye.
See you. Bye.
Bye.
Thanks.